Okay, hello. Good evening, everyone. Okay, so for today's session is going to be, I think, fairly short with the quiz discussion. All right, so after that, we can continue with discussing anything that you have for the midterm. All right, those topics for the midterm. Okay, so let me start, and I think we will first go through some other stuff, which is the mid semester survey that we did. Okay. Yeah. So before that, so this Saturday is your midterms. All right. So as you know, it is face-to-face at MPSH. Okay. So yeah, we had no choice because the school was quite clear that we should not have any online assessments and everything should be face-to-face. Okay. So that is that, and yeah. So the consultation sessions lined up for you. So tomorrow there is one with Colin, all right, 7:30 to 9 over Zoom. Okay. Then Boo has also set up, I think he sent an announcement for a doodle link, all right, to pick any slot, okay, where you can go and consult him. Okay. For myself, I will have it on Friday, 4 to 6 at the makerspace. Okay. So I hope you know where is the makerspace. It is at Com3. Okay. Yeah, if you're not very sure, it is just behind that what shop? I think that yogurt shop or something. Okay, so it's just behind that. Okay, so you just can come there. Just give me a minute. Okay, sorry about that. Okay, so yeah, so this Friday, 4 to 6, so I'll be at the Makers Lab. Okay, so if anybody wants to consult about anything, you can come there. Of course, prior to that, you can always WhatsApp me if you have anything you want to discuss, okay, or you want to clear any doubts. Okay, so I will not go through the details. I think we had a sort of mid-semester survey, correct? Of course, the number of respondents is also quite low, only 109 out of sort of 662 of y'all. Okay, so it's also a bit difficult to gauge the actual sort of sentiment on the ground, correct? But I'll just roughly go through the results. Okay, so in terms of lecture videos, I think most of you appreciate, okay, the lecture videos that have been recorded and given to you for viewing. Recitation, okay, again, most of it found it useful. All right. Okay, so of course there are some who say it's not so useful and you don't recommend it and so on. Okay. Quizzes wise, I think most of you are quite supportive of it, which is good. All right. Again, the main aim of the quizzes is to sort of make sure that you see the content and you try to absorb as much as you can, okay, from the material that is already presented to you before the recitation. Okay, and blended learning is again 50% only feel that it's sort of working out. All right. Yeah. So the weak points, okay, in general from the survey is that recitations and blended learning. So these are sort of the 2 points of concern. All right. And I think some of you also have brought out some feedback that the modular credits is too low for the amount of workload, okay, that you have and so on. But again, these are things that are beyond our control, okay, because, you know, at the sort of planning level, there are certain credits that students need to graduate, okay. So if you increase one module, then somewhere we need to decrease, and that leads to other complications, okay. So it is not something that we can just easily do, okay. It requires a lot of planning and may not also happen. Okay. Factors within our control is of course lesson activities, blended learning. Okay, so again, this one I will not comment too much. Like I said, I'm only doing this for this semester alone. All right, so probably Colin and Prabhu will follow on these to see what else they can do to improve or change the way lessons are done. Okay, so yeah, so I will not go through the summary slides here, okay, because these summary slides are basically the full sort of extracted from whatever that you have covered in class so far. Okay, so what I will do is I'll go straight to the discussion on the quiz questions, and from there I think we'll be able to sort of also address some of your questions and doubts that you have. Okay, so again, these are fairly simple questions. I think within less than an hour we should be done. Okay, and then we will discuss other stuff. Okay, so before any questions, you feel free to just put in the chat, or you can just voice it out. Okay, so here we have two expressions. Okay, expression 1 and expression 2, and they asked we asked to check whether they are equivalent. Okay, so as you can see, expression 2 is the simpler one. Expression 1 is the more complex one. So we always try to work from the more complex one towards the more simpler one. All right, and try to see whether they match. Okay, so if I look at the more complex expression over here, okay, so what I have is x bar. Okay, okay, so I always like to put a bar instead of the sort of complement or the dash sign at the side. Okay, because I think it's easier for me to see and less prone to mistakes. Okay, but again, this is just a personal preference. Okay, z plus x z. Okay, and this whole thing has a bar. Okay, so if I look at this expression, so since the expression 2 already has x bar here, I will leave that x bar out and I'll focus only on the bracket. Okay, I'll focus on the bracket. So for the bracket wise, okay, we can see that this one I can simplify as y plus y bar. So z plus xz is equivalent to z. Okay, so that is your absorption law. Okay, absorption law. So this z plus xz is equivalent to z. Okay, and so this bar here is for the whole thing here. Sorry. Okay, so this is what you have here. Okay, and then y plus y bar z. Also, I can use another absorption law, which will be y plus z. Okay, so this is also absorption 2. So you can look back at your slides. Okay, so beyond this, you can't really simplify anymore. So you still have x bar. Okay, and this expression is on the other side. Expression 2 is x bar y plus z. Okay, so you can see that they are not the same. Okay, they are not the same. So the answer for this is no. Correct, they are not the same. All right. So the tricky part of using these laws or rules to do simplification is that sometimes you reach a point, okay, and then you do not know how to carry on, but actually maybe there is a way to simplify, okay, but you just do not realize it, and then maybe you're not sure which rule to use, and you think that is the final one, okay. So that is why the K-maps, okay, which we will do later, are sort of the more ideal way of getting the most simplified expression, okay, because with K-map, as long as you apply the rules correctly, you will get the most simplified expression, okay, once you do that. Okay, now let's look at over here. So here, again, we have two expressions. We want to work from the more complex expression. So that complex expression is this. So x plus, dot y plus yz plus z holding bar. Okay, so again, I will leave the x aside and focus on this bracket portion. So y plus yz will be equivalent to y. Okay, so that is your absorption law. Okay, so that is your absorption. Okay, and y plus z bar, I can apply De Morgan's theorem. So De Morgan's theorem basically says that the or and n are interchangeable by breaking the bar. So this plus will become a dot and I break the bar. So it'll become y bar and z bar. Okay, so that is your De Morgan's theorem. Okay, and then I can put the x back here, and the expression 2 is x dot y bar dot z bar. So they are both the same. So the answer here is yes. Okay, so let's look at the next one. Okay, so we have the following functions, and we ask which of the following products are not in the canonical sum of products, okay, for f. Okay, so I will sort of show you the proper way, okay, and I'll show you a shortcut way, okay, and then you can see which one you sort of prefer, okay. So the proper way is, of course, you apply the rules, okay. So if you apply the rules, okay, you get b dot c plus a dot b bar. Okay, so the first thing is we can see that originally we have three literals, correct? A, B, and C. Okay, but in both this expression we have one short of it. So in the first one, A is missing. The next one, C is missing. So the first rule we can apply is what we call the identity rule. Okay, where we add a 1 to represent the missing literal. So 1 is equivalent to A. In this case, any literal add with its complement is equivalent to 1. Okay, so 1 can be written as A plus A bar dot B dot C plus over here A B bar dot C plus C bar. So again, on the first left hand side, A is missing, so we replace the 1 with A plus A bar. On the right hand side, C is missing, so we replace it with C plus C bar. Okay, and then finally we use the distribution rule to say A B C plus A bar B C plus A B bar C plus A B bar C bar. Okay, so that is basically the distribution rule. So identity rule, then the complement rule, okay, and then the distribution rule. Okay, so these are the sort of proper way of doing it, applying the rules. Okay, now what is the sort of shortcut, okay, to solving this is you just look at what is missing, correct? So you know that over here A is missing, correct? So when you say A is missing, it implies that A was simplified out of the expression. Okay, so if you say that A was simplified out of the expression, it also sort of implies that it doesn't matter whether A was 0 or A was 1. Okay, so that is the thinking. Okay, so A was simplified out of the expression. So A could have been 0, it could have been 1, it makes no difference. Okay, so that means I can say that this expression is equivalent to saying I have A or I have the complement of A. And similarly here, C was missing. So C could have been 0, could have been 1, makes no difference. So I have A, B bar, C, and A, B bar, C bar. Okay, so it's the same answer. Okay, the same answer. Okay, only thing here, you just think through what would be the answer, then you apply the rules. Okay, so that is, of course, I will always use the shortcut method. Okay, but if you want to use the rules-based method, you can still get the same answer. Okay, so that is this question here. Okay, so I'll just go on. If I don't hear anything, means I assume that there is no questions. Okay, if you have anything you're not sure, please just ask. All right, now for this, again, the same thing. We will first go by the proper way, okay, applying the rules. So this expression is x plus y bar, okay, and y plus z. So this is the product of sums, all right? So in this case, instead of adding product 1, we all with a 0 to represent the missing literal. So here I'll say the x plus y bar plus 0 dot 0 plus y plus z. Okay, and the 0 is represented by the complement rule. Let's say is equivalent to z dot z bar, and here is x dot x bar plus y plus z. Okay, and then from here you can sort of expand using the distribution law. So you'll get x plus y bar plus z, x plus y bar plus z bar, then x plus y plus z, and x bar plus y plus z. Okay, so let me write the laws here. So the first one here is the identity. Okay, then the complement, and then the distribution. Okay, so like what we did earlier, you can apply the same sort of shortcut method of solving it. All right, so here again the same thinking. So z is missing means z could be 1, z could be 0. So I can say that this is equivalent to plus z or plus z bar, and over here it's the same thing. X is missing means x could be 1 or x could be 0. Okay, so you get the same answer here, same expressions. Okay, so that is how you can solve this. Okay, so from there you know what is the answer. Okay, so let's move on to the next question here. So next question asks you for the expression, okay, the final expression. So we can do this step by step. Okay, so the first thing here is okay, so from complement to distribution law. Okay, so the distribution law, okay, you can view it this way. Okay, you can say that, for example, A plus B dot C is equivalent to A plus B and A plus C. Okay, so in a sense, you can think of it that B dot C is equivalent to this, and A is basically represented by this x plus y bar. Okay, so it becomes x plus y bar plus z and x plus y bar plus z bar. Okay, so in the law, though they say you put a single sort of literal A, that A could also be a combination like this x plus y bar. So that's how you apply distribution law here. Okay. Okay, so let's look at the next question here. So this is the quiz 2. So in quiz 2, you're asked to find the expression. Okay, so the input here is x. So after I go through the NOT gate here, I'll get x bar, and here will be y. So this will be x bar dot y, okay, which comes here. And the same x bar is connected here. All right, so over here, what I'll get is x bar plus x bar y, and this is a NOR operation. Okay, and then I have a final OR with a z. So the final expression here is z plus x bar plus x bar y, and I get this. All right. Now, to simplify this, I can say that this is, I can straight away use the absorption law. So x bar plus x bar y will be equivalent to x bar. Okay, and I have one more bar on top, which means this is z plus x. Okay, so that is how you can get the final expression here. Okay, so I think that should be quite okay. Now the last one is the propagation delay. All right, so we know that each of them have some delay. Okay, so in reality, okay, when you do the lab, okay, you might not see it in the lab, all right, but in reality, every component here has a finite amount of delay before the output is triggered. Okay, so for example, if I have a NOT gate here, X, okay, so if this is X and the signal changes, the output of X, which is X bar, okay, theoretically, we draw it this way. Okay, theoretically, we draw it this way. Okay, but in reality, this is not the case. In reality, it will be, okay, a bit later. That means the output will actually change a bit later. Okay, because of what we call the propagation delay between the input and the output. That's the time taken by the circuit to generate the new output. Okay, so what we are given here is the NOT gate has 1 nanosecond, the AND gate has 2 nanosecond, the OR gate also has 2 nanosecond, and the NOR gate here has 3 nanosecond. Okay, so in terms of delay, okay, we need to look at the maximum between the all inputs. Okay, so if you take X for example, X after propagating to the NOT gate would be X bar. Okay, so for the AND gate over here, it needs to wait for X bar and Y. Correct. So since it needs to wait for X bar and Y is available immediately, but X bar I need to wait for 1 second. All right, that means in terms of time, from this point to this point, I would need to wait 1 nanosecond for X bar to be generated. All right, it's the maximum amount of time. So even though Y comes there first, I still need to wait for X bar to be generated before I can get the correct output from the AND gate. Okay. Now, when the AND gate generates, it takes 2 nanoseconds. Correct. Now, if I look at the input of this OR gate over here, if I take this point over here, the inputs are X bar and the output of the AND gate. Now, X bar is generated after 1 nanosecond. Okay, but the other input is generated only after the AND gate. So I need to wait, okay, 2 nanoseconds after X bar is done. So I need to add on to this. Okay, because the first 1 nanosecond is for X bar, and I need to use X bar in the AND gate. All right, then only the inputs are ready for the NOR gate. Okay, and then similarly, when the NOR gate processes this, it requires 3 nanoseconds. Okay, so even though Z is available immediately, I still need to wait for the output of the NOR gate to be generated before I can proceed on to the OR gate. Okay, and finally, I have the last one, which is 1 nanosecond. Okay, for the OR gate. Okay, this is so total of 8 nanoseconds. Okay, now the thing about combinational logic circuit. Okay, so I'm not sure. I don't think you have studied it yet, but we have combination logic circuit. Okay, and you will probably be studying it in the next week, which is sequential logic circuits. The difference is sequential logic circuits have a clock. Okay, similar to your processor, correct? You have a clock-based system. That means when the clock triggers, something happens, you propagate the signal through the whole circuit, and then you get the output before the next clock comes. But in a combination logic circuit, everything just flows. Everything just flows, okay? The moment input changes, okay? Which means that if I have my X, Y, Z, and I say this is time, see what happened here. Okay, so if I have my signals X, Y, Z, and I say at time t equals to 0, I provide some input. Okay, it means that I should only read the correct output after 8 nanoseconds. Okay, during this time 0 to 8, things will change. So maybe, okay, at some point of time, this output here. So if I call this output P, okay, the output P may change from 0 to 1, 1 to 0 in between this period here. Okay, depending on what is happening through these gates. Okay, but we do not worry about that. As long as we know that this is the time where we should read the output, then we take that value as the correct value after the factoring in the propagation delay. Okay, so again, these are implications for a real world circuit, okay, where we need to take into account this time, right? And this is the same thing in our Mips processor as well, okay? If you remember in Mips processor also, we say that many things happen in parallel, right? Everything happen in parallel, but then because, okay, of timing, okay, and the multiplexers, we always make sure that the correct data is available at the correct time to move it through, okay, to move it through to the next stage and so on. Okay, so that is how you sort of make sense of this. Okay, so the answer is 8. Okay, now we're in the last two questions. Okay, so it's faster than I thought. Okay, so the last two questions is on K-maps. Okay, so suppose use K-maps to simplify this expression. Okay, so we have 3 inputs. Okay, so we have 8 possible sort of values. So to draw a 3 input K-map, you can draw it sort of horizontally or vertically, up to you. Okay, so I'm going to just show you how I do it. And if you think that this way is easier or it's a bit different, then you can decide between this and whatever that is shown in the lecture slides or whatever. Okay, so what I will always do is, again, it could be vertical, it could be horizontal. Okay, and then you list out the possible values. So X, Y. Okay, so the key thing to remember in K-maps is that adjacent rows or columns must always differ by only 1 bit. Okay, not by more than that. So we always start with 0, 0, 0, 1, then 1, 1, 1, 0. Same thing here, 0 and 1. Okay, and what we do is we look at these expressions. Okay, so the first one is Y bar, Z bar. Okay, so Y bar, Z bar. Again, like I said earlier, if I don't see one of the expressions, means that expression, if I don't see one of the literals, means that has already been simplified out, which means that this is equivalent to having either X, Y bar, Z bar, or X bar, Y bar, Z bar. Correct? Okay, so that means it's equivalent to 1, 0, 0, which is this. Okay, so I'm going to put a 1 here, or 0, 0, 0, which is this. Okay, so that is the first thing. Okay, for the next one, X bar, Y bar, Z. So that one is already having all 3. So it's straightforward. So it'll be 0, 0, 1. So 0, 0, 1 is this one over here. Maybe I'll use this color. Okay, then the next one is X bar, Y. So X bar, Y, again, as we said, Z is missing. So it is X bar, Y, Z bar, or X bar, Y, Z. Okay, so that is equivalent to 0, 1, 0, which is this, or 0, 1, 1, which is this. Okay, and the last expression here is x, y, z, which is 1, 1, 1, which is this. Okay, so that is the first step. Okay, given the expression, you fill up the K-map. Okay, and once you fill out the K-map, then the rest is just grouping based on the rules. So the rules is always based on powers of 2. Okay, and of course, I think in the lecture slides, you already have all those things that you can and cannot do. All right, so in terms of grouping, we can do one big group over here. Okay, now for this group, how do you write the simplified expression? You look at the what changes and you remove what changes. Correct. So you can see that this group occupies 2 rows. And if I look at the first row and second row, y changes. Okay, y changes from 0 to 1, but x stays the same. So I will keep x. Okay, y changes. And similarly, from first column to second column, z changes. So I also discard z. Okay, I discard z and discard y. So left is only x bar. Okay, so that is the first grouping there. Now for this one here, the only possible grouping is this. Okay, so that will give me, so for this, you can see that from row, the second row and third row, x changes. So I discard x, I keep what is constant, which is y, and z is constant, so this is yz. And for the last one is, I can do a wrap around. Okay, so I can wrap this with this. Okay, so that will give me y changes. So the first row and the last row, y change, sorry, x changes, so x disappears, y remains, so is y bar, and z also remains, so is z bar. Okay, so that's how you get the final expression, which is x bar plus yz plus y bar z bar. Okay, any questions on this? Okay, if not, I'll go on to the next one here. Okay, so in the next one, it is the same expression. Same expression. Only thing we are going to find the POS. Okay, so what is POS and SOP? They are both is the duality principle, correct? So SOP, any expression you can express in SOP, you can express in POS. Okay. Again, it is just a matter of how you want to design the circuit. All right. Right now, you might think, why must I bother with both? All right. But later on, when we look at the other use of combinational circuits, okay, like multiplexers, decoders, and so on, you will see that in some instances, if I implement my circuit in one of these forms, either SOP or POS, I may get a much simpler circuit, okay, compared to one that may involve the other form. Okay, so maybe this example may not be so obvious, but you will see that more clearly as we go along. Okay, so I'll use the same truth table here, I mean the K-map here, and here what we have is for POS, we group the zeros. Okay, so I'm going to put the zeros first. So this is 0 here and this 0. So as you can see, both these zeros are positioned such that there's no way that they can be grouped and they can be simplified. Okay, so there's nothing you can do. So this is one group and this is one group. Okay, so basically what you have here is this expression, which is x, y, and Z bar. Okay, so I'm going to show you two ways. Okay, two ways in which you can come up with this POS form. Okay, SOP is quite straightforward, right? The POS is, there's two ways. One is you start with SOP and then you use De Morgan's theorem, or you straight away do POS from the zeros. Okay, so let me show you the first one first. I start off with SOP and then convert to POS. So if I start off with SOP, okay, start of products, then this will be X bar Y, sorry, X, Y, and Z bar. Okay, and this will be X, Y bar, and Z. Okay, X, Y bar, and Z. All right, now these are zeros, correct? I'm grouping zeros instead of the ones. So because I'm grouping zeros, this is considered, okay, so let's say this is F. So this is actually considered F bar is X, Y, Z bar plus X, Y bar, Z. So I'm writing the SOP form, but this SOP form is not for the actual F, it's for the F bar because I'm representing the zeros and not the ones. Okay, now if I want to convert this to F, then I apply De Morgan's, I can invert this. So I also invert this. So F double bar becomes F. Then this I employ the De Morgan's theorem. So this plus will become a dot and this will become X, Y, Z bar and X, Y bar, Z. Okay, and then I apply De Morgan's theorem one more time here. So I'll get X bar plus Y bar plus Z double bar dot X bar plus Y double bar plus Z bar. Okay, so the double bars you can comes back to the original literal. So X bar plus Y bar plus Z dot X bar plus Y plus Z bar. Okay, which is what you have here. Okay, so that is one way of doing it. That means you write out the SOP first, okay, but the SOP is actually for the F bar and then you invert it to get F. So on the other side, you apply De Morgan's theorem to come back to the answer. Okay, now the other way, okay, the other way of looking at it is, okay, so maybe let me just draw the, okay, so the other way of looking at it is I straight away express it based on what is given. So if I look at this, this 0 is X is 1, Y is 1, Z is 0. Okay, again, this is based on the current K-map, correct? But since we are doing it in POS, we just invert it, okay? Because in POS, we're looking at the 0, so we invert everything. So the 1s will become 0. So in terms of X, Y, Z as 1, 1, 0, it will become X bar, Y bar, and Z. And instead of AND operation, you replace with a OR operation. Okay, same thing over here. This one will become X, Y bar, Z, but now you write it as X bar, Y, and Z bar, and you replace it with a OR. Okay, so you get the same answer. Okay, so the answer will be this expression dot with this expression. Okay, so there's two ways of doing it. You can directly interpret it, okay, by flipping the bits. So the ones become 0, 0 become 1. And instead of a product, you write it as a OR operation. Okay, or you can do the SOP expression and then you flip it after that. Okay, either way, you'll get the same answer. Okay, so I think that that's the end of the quiz questions. So anything that you want to ask first about the quiz? Okay, so let me go back to the slides here. Let me see what else. Yeah, so I think we sort of covered what I want to discuss. So I will open up now to discuss anything else that you have in your mind that you want to ask, either about these topics or about the midterms or anything that you want to discuss. Okay, let me just go through the Slido questions. Okay, so these are some of the Slido questions. Okay, so why expression 4 and 6 aren't SOP after applying distribution law? Okay, so we say whether they're SOP or not, or POS based on what is given. Okay, not what it could become if you apply rules and modify them or so on. Okay, so given the expression, then you say whether it is SOP or POS. Okay, so that is this. Programmable logic arrays. Okay, so what does it mean by connection between input and plane can be burned? All right, so basically a programmable logic array is one where you already have pre-built circuits, okay, with OR and 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 so on, okay, and they will sort of give you a way to burn the connections. Okay, so what do you mean by burn connections? So let's say I give you this expression, okay, so I say X, sorry. Okay, so let's say this is the one, right? And let's say I give you this expression. I say Y is equals to, I don't know, okay, P is equals to X bar Y all with Y, Z, okay, plus X, Y, Z, X, Y bar Z, something like this. If I give you this expression, of course, you can use your AND gates, NOT gates, and so on to solve it, okay? But if I use something like this, okay, what I will do is I will burn the connections based on the input. So what I will first do is I will set aside inputs here. So this is X, Y, Z. So if this is X, okay, so X comes here. So you have to understand X comes here and X bar is here. Similarly, Y comes here, Y bar is here, Z comes here, Z bar is here, correct? Because of the NOT gate. Okay, so maybe I should draw it here. So what you get here is X, this is X bar, this is Y bar, and this is Z, this is Z bar. Okay, so if I wanted to have X bar dot Y, what I will do is I will burn this, okay, and burn this. So it will be X bar Y. So this input here would be X bar Y, the output here. The output of this AND gate will be X bar Y. Okay, if I wanted to create YZ, then I will burn another row. So this will be Y, and this will be Z. So the outcome of this AND gate will be YZ. And if I wanted to create this X, Y bar Z, I will take another row. So I'll say this X, and this Z will be burned. So this will be X, Y bar, Z. And then what I will do, since I need to OR them together, I will burn this, burn this, burn this, because this is OR, correct? So the outcome here would be P. Okay, so that is how this programmable logic arrays work. So it's like a matrix of interconnections already there, and then you decide what you want to burn, what you want to keep open, and so on. Okay, so depending on the expression that you have. Okay, so this sort of in a sense makes it a bit easier so that you don't need to physically hand wire a lot of things together. All right. But again, these are older tech. All right. Nowadays we all use FPGAs to program hardware. Okay. Which makes it a lot easier and more efficient. Okay. So that is how this thing works. Okay, so I think KMS we went through just now, the SOP and POS and so on. So I think we need to go through that again. Okay. Yeah. So anything that you want to discuss? Any questions about the midterms or any concerns you have from the previous tutorials? Okay. So you're going to cover. We're going to be covering everything. Okay, all the way to the end of Mips. Right. It's all the under control. Okay, for the midterm, it's MCQ. All right. Yeah, I think you have 1.5 hours or something like that. Okay, so like I said, I will have the consultation session on this Friday, 4 to 6. Okay, and yeah, I mean, if nobody turns up, you know, if I'm there and nobody turns up, then probably by 4:30 or so I'll leave. Okay, so I will not stay there for the whole time. Okay, I will stay around probably for an hour, okay, 4 to 5. And if nobody turns up, then I assume that nobody needs help, then I will leave. Okay. Okay, midterm 2018 SEM 2 question 10. Okay. Okay, midterm 2018. Okay, can you send me the link where I can add the question again for the midterm? Is it this link? Is it the top link? Yeah. Okay, let me go and check, download the question first. Um, (2018) SEM 2 question 10. Okay. I think this question I need to look through the whole thing. Will take some time. Okay. Any other questions first? Because that question I think I need to go through the whole question first before I can understand and answer. Okay, so besides that, any other questions that you want to discuss? Sem 2021, Sem 1 question 15. Okay, give me a minute. Okay, give me a minute. Let me download it. Sem 1 question 15. Okay, so question 14 from the answer sheet or from the, because it seems to be a bit different in the question paper and the answer paper. Wait, let me share the screen first. Is it this question or the other one? This question, is it? Okay. So the Mips Slt instruction takes the form. Okay, so basically we have SLT operation. Okay. So the set if less than is to perform subtraction operation, correct? So that you know whether the answer is negative or not. Correct. Okay. So the SLT operation is basically to perform that. Now, when we perform a subtraction operation, all right, the most significant bit will give us the indication whether it's a negative answer. Correct. So in this case, okay, the first thing is okay, let's look at what are the options here. Okay, why these are the ones that are needed to implement the SLT instruction. Okay, so the ALU control. If I say 0011, that means how do I do this? Okay, let me slice this first. Okay, so what I want to do is I want to take A and I want to subtract B. All right, so when A subtract B, I'll get an answer. Okay, and this answer this most significant bit, that means bit 31, will tell me whether the answer is if A is smaller than B. All right, if the bit 31 is set, that means a negative answer, a negative value. So A is smaller than B. All right. So what I need to do, I need to do a subtraction operation. Okay. So which means that this has to be 0, 1, okay, 0. Sorry. And the operation here should be, so this is 0, 0, 0, 1, 1, 0, and this is 1, 1. Okay, so this should be the value of the ALU control. Okay, because now you have a 4-bit input. Okay, so that is why this answer is F here. Okay, because we are trying to do A subtract B. Okay, now the next one. Okay, so this is not correct. Now set the 0B on input of the ALU slice for bit 31 to the output of the adder of the bit 0 ALU. Okay, set the 0BB11 input of the ALU slice for bit 31 to the output of the adder of the bit 0 ALU slice. Okay, now this slice is what? This ALU slice for bit 0, bit 31. Basically, what they're saying is, if you remember, we said that ALU is implemented in this case bit by bit, correct? So bit 0, bit 1, bit 2, all the way to bit 31. Okay, now what we want is when this answer is 1 or 0, okay, it will indicate whether it's less than or not. All right, but we want this to be reflected, okay, as an answer which is in the bit 0 of the outcome. Okay, why? Because when I do the SLT operation, okay, what I want is the outcome should be either 0 or 1. This 0 or 1 is based on reading bit 0 of the result. Okay, but the result after the subtraction operation, the result that I'm interested in is actually bit 31. Okay, it's bit 31. So for bit 31, it will come to bit, I need to move it to bit 0, and I need to make all of this 0. So the outcome of SLT will be either 0 or will be 1, depending on the bit 31 value after I perform the subtraction operation. So what I need to do is, I need to take the bit 31 value and put it to the bit 0 value. Okay, so that is why they say that I take the output, okay, of the bit 31 and set it as the input of the ALU slice or bit 0 and set all the remaining ALU bits to 0. That's why this is the answer. Okay, so the idea is when I perform the subtraction operation, okay, if A is really lesser than B, then this implies that bit 31 will be 1. Okay, but what I want is bit 0 should be equals to 1. So I must translate this. Okay, and all the other bits in between must be 0. So that will give me, so when I do this, this is what I'll get. Okay. Okay. Is that clear? Okay, why is it the operator? Okay, so this operation 0B11 is referring to the multiplexer. This multiplexer here has 4 inputs. Correct? Has 4 inputs here. Okay, the first one is the AND gate. The second one is the OR gate. The second one is the ADD. And now we have added the fourth one, which is the SLT. Okay, so that is why this is 0001 1011. Okay, so this 0B11 is referring to the multiplexer setting. So what they are saying is set the 0B11 input of the ALU slice for bit 0 to the output. So what we are saying is that this 10 here, okay, will actually go directly to the of bit 0. Okay, that means you will go directly to the bit 0 ALU slice for the operation 11, which is the SLT selector. Okay, it is okay. Any other questions on this? Why isn't the operation bit 10? Okay, so again, the subtraction, okay, is done. All right, the subtraction is done. Okay, so basically, what the way it is done is that you see the operation of how to put it. Okay, the subtraction, okay, would still be carried out, okay, regardless of the operation. Correct. If you remember, we say that all of these are considered combinational logic. That means as long as A invert is 0, B invert is 1, what goes through is A and the invert of B, which means that for all the bits, all the 32 ALU splices, I will perform the subtraction operation. Okay, I'll perform the subtraction operation. Okay, but I'm not interested in the subtraction result. Okay, I'm not interested in subtraction. If I'm interested in subtraction result, then the operation bits would be 1, 0. Okay, but I'm not interested in subtraction result. I'm only interested in the bit 31 of the subtraction result. Okay, so basically what we are doing, okay, so if you think about it this way, okay, if I were to draw all the blocks here, imagine this, okay, so these are all my ALU splices. Okay, 31, 30, 29, all the way to bit 0. Okay, and each of it has my inputs A and B coming in. Okay, and all of them are doing my subtraction operation. Okay, but I'm not interested in subtraction result. Okay, after all the subtraction is done, I'm only interested in this answer. Okay, I'm this in answer. So what I'm going to do is I'm going to take the output of the adder bit of bit 31. That means in each of this, I have the adder bit here, correct? So I'm going to take the output of the adder bit, okay, and connect it such that there is a special line that comes all the way here and comes here. And inside this bit 0 is where I'll connect it to this point here. And I take the result from here. Okay, that is how this solution is designed. Okay, so I'm performing subtraction, I'm performing AND, I'm performing OR. Okay, but I'm not interested in all of that. I'm interested in the subtraction, but only in the bit 31 result. Okay, so I don't think we covered 3's complement, so I don't think we need to worry about this. Question 6 and 7, yeah. Okay, so the other question on the (2018 Sem 2). Okay, the 2018 one, that one, I think I have to spend some time to look at the whole question first. All right, so maybe I will work it out, and then maybe you send me an email, and then I will update you on it. Okay, so Okay, so tutorial 5, question 2A. Okay, give me a minute. Okay, so let me share this. So this is the question, correct? 2A. Okay, so here is the subtraction instruction, correct? So we are trying to analyze the total time it takes, correct? So the first one is we fetch from instruction memory, correct? Okay, so that is 400 picoseconds. So once we fetch from instruction memory, we immediately extract. Okay, so all these are hardwired, correct? These bits from the instruction register to the register file, they're all hardwired. So I straight away extract this and I can start to process the data to access the information in the registers. Okay. At the same time, all right, the control also is being triggered. Okay. And what happens is, okay, the control block, as you can see, is very fast, 100 picosecond compared to the registers. All right. So I don't need to worry about the control because it is able to process it much quickly compared to the register file. So all the multiplexers all will get the correct information ahead of time. Okay. So after the register file, then I need to go through the mux. Okay, the ALU source. All right. So if you look at the ALU source, okay, you basically have the RD1, the RD2, and the immediate value. Okay, so this is the ALU. Okay, so the ALU takes another 120 picoseconds. Okay, now why do you need the ALU here? Okay, because this instruction was this was the R-type instruction, correct? This is R-type instruction. So this was the R-type instruction. So because the R-type instruction, I need to have both my registers information before I can process the data. Okay, so I need to wait for my multiplexer here to channel the right data through before I can perform the ALU operation. Okay, and then I perform the ALU, and then after the ALU result is obtained, then I go through the multiplexer, and after I go through this multiplexer, then the data is sent back to the register file for the final write back. Okay, so that gives us the total amount of time from the start till I complete. Okay, register destination is not included because this write register information is only needed when this data comes back. Okay, so even if I say the same time marks is 30, so if I take 30, what is the significant thing? All of this came in at time 0, at time 400. Correct, because after I fetch the instruction, this one came in at 430, but no big deal, correct? Because this data only comes in at the end after I complete this part here. So I still have to wait for all of this anyway. So even though there is a delay there, you don't need to factor that in because you only need the information towards the end. Okay, so yeah, so I think the other question I need time to go through, all right, because it's quite a long question, all right, and then yeah, so I don't want to hold out everybody here. So let me go through and then I will reply to you. Okay, so that's all I have. Okay, so the if SLT output is 1, okay, so if the SLT operation carries out and A is indeed lesser than B, then for bit 0, the outcome of bit 0 will be 1. Okay, because the operation bits will be set to 1, 1. Okay, because bit 31, which is sort of holding the end bit, the most significant bit, will be mapped back to the multiplexer of bit 0. Correct. So if the outcome is truly less than, then the bit 0 output will be set to 1 because the multiplexer's operation bits will be set to 1, 1. Okay, so I think no other questions. Like I said, if anything else, we can email me or WhatsApp me, or you can talk to me on Friday. Okay, so thank you. I'll see you all.